Hello, everybody. This is Team 3 checking in, and our title for our experiment is Growth of Extremophilic Bacteria Deinococcus radiodurans in Various Viscous Fluids in Space. And our group is made up of 5 people: Adam, myself, Chris, Nathan, and Rayshaun. Our research question is, how would Deinococcus radiodurans grow within 2 mediums, silica gel and water, under effects of microgravity?
So looking into the background of our experiment, our bacterium that we chose is Deinococcus radiodurans. Deinococcus radiodurans is a polyextremophile bacteria. Being an extremophile, it can survive in extreme conditions such as microgravity, as well as extreme temperatures and especially significant radiation. One contributing factor to its survival is the robust DNA repair mechanism, which allows for consistent cell functionality even when the DNA of the cell is damaged.
So looking at our fluid mediums, we chose water for a low viscosity medium as it is one of the most common liquids found aboard the ISS. The way the ISS gets its water is through a recycling process known as the water recovery system, which takes liquids from astronauts, such as urine, sweat, and even condensation for breath, and recycles it through a process which filters out and kills almost all microorganic contaminants. However, D-radiodurans' extremophilic nature makes it a good candidate to test growth after going through this process. We chose silica gel permeated with water as our high viscosity medium due to its importance aboard the ISS in oxygen recycling. The ISS has an oxygen filtration system known as the carbon dioxide removal assembly, which takes breath exhaled from the astronauts and removes the CO2 from it. It first uses beds of silica gel to remove all moisture from the oxygen, as the CO2 removal part is sensitive to moisture. This process hits a temperature of negative 90 degrees Celsius. However, D-radiodurans are able to survive the vacuum of space, which is far colder.
So within our FME design, Ayush, can you hit it twice? Within our FME design, volumes 1 and 3 will be our experimental volumes, holding our bacteria within the 2 mediums that we have chosen, water and silica gel. We have split our volume 2 into volumes 2A and 2B by using a 3D printed partition. This will allow us to have 4 volumes in total, 2 volumes holding a fixative, 2.5% glutaraldehyde, which will react with the experimental volumes and cease cellular activity without killing the bacteria. This allows us to essentially save our bacterial concentration data so we can analyze it with optical density spectrophotometry when the FME returns to Earth. All FME tubes are 9.5 millimeters in diameter. Our partition disc will be difficult to fit in the FME tube as it's the same diameter, but the stretchiness of the silicon material will allow us to fit the disc in. Once it's in place, we will add Master Bond's polymer system EP29 LPSB adhesive, as it has low outgassing properties and is approved by NASA. We will run the equivalent control experiment at the same time on Earth.
So in reference to the applications of this experiment, I just want to say that several more, commonly found species of bacteria have been found and studied on the ISS more extensively. However, extremophilic bacteria such as Deinococcus radiodurans are still being studied under certain conditions. What we hope to learn is, we hope to learn more about both the chemical and physical limits of life, especially in reference to extraterrestrial environments, and hope to apply this knowledge to more commonly found species and various microgravity environments.